Let's do some applications. What if you have an infinite line of charge? We already know what the electric field should be. We want to see how you can get it from Gauss law. Let's say you have infinite line of charge which has linear charge density lambda. We want to see what is the electric field of this line of charge at distance r, let's say, from that line. If you want to use the Gauss law, we need to use a Gaussian surface. And if you want to calculate the electric field from the Gaussian surface, the surface should be very symmetrical so that you can take care of that integral on the left. So it is very crucial to use the right Gaussian surface, because although Gauss law is correct for any surface that you take, it may not help you if you choose the wrong surface. And usually you use symmetry to simplify that integral and be able to get the electric field from there. All right, in this case, we need a symmetrical Gaussian surface so that we know what happens to E dot dA at any surface, any part of the surface. For example, if you have the this line, because of symmetry, you know that the electric field is always either away from this line or toward the line. It cannot have any azimuthal component to the line. Because if it has azimuthal problem, it breaks the symmetry. So if this is line of charge, you have this, and the electric field at this point is like that, this distinguishes this direction from the other direction. So that breaks the symmetry. So because we have symmetry, we know that at any point around this line of charge, the electric field is radially outward from the line. And we want to make a surface that simplifies the integral. So what kind of surface would you take so that the E dot dA is easy to calculate? I would take a cylinder. And because the electric field is radially outward, and at this side the electric field is this way, which direction is the dA that I calculate? Yeah, it's outward from this cylinder, so it's parallel to the axis. So this is dA, and this is E. We know that should be outward because of the symmetry. So E dot dA will be 0 at this point. And all of the pieces of this surface, the E dot dA is 0. And the same here, right? So E dot dA only has value on this round part of the cylinder. And at any point, you see dA is like that, and the dA is outward, and the electric field is either outward or inward. Let's say it's outward now. E is also in this direction. Both of them are in the same direction. So we can use this symmetry and simplify the integral. We say that integral for this surface, integral E dot dA equal to total charge inside divided by epsilon naught. This is Gauss law. But because we know that on this cylindrical surface, E and dA are in the same direction, E dot dA just becomes magnitude of E times magnitude of dA, right? So the dot product becomes just simple product. The integral over the surface, E times dA, equal to Q inside over epsilon naught, right? Does it make sense? Using symmetry argument? Okay. Now also we know that if it's a cylinder of certain radius coaxial with the line of charge, the electric field on the surface is the same everywhere, isn't it? Because there's no distinction between one point to the other. They're all the same. So the electric field is the same everywhere on the surface, has the same magnitude. Of course, different directions, but the same magnitude. The directions are always in the direction of dA. That simplifies it to this. But E is also constant and can come out of the integral. This is how we use the symmetry to simplify the integral. This becomes E magnitude times integral of dA. And we know that only contribution to the round side of the cylinder, not the two lids on the sides. So the integral of dA equals to Q inside over epsilon naught. Now, what is the integral of dA in this case? Let's say this cylinder has the length L. What is the area of this cylindrical surface? If it has a radius r and length L, what is the area? So we have D times the area. If you cut it and open it, you said one side is the circumference of this circle, right? It's 2 pi r. The other side is L. So 2 pi r times L. Right? That's the area. So that's this integral simplified to that. And how much charge is inside this? How much charge is inside this cylinder? Is it from here to here? It has charge per unit length of lambda, right? Lambda means this charge divided by the length. So the charge is lambda times L, right? So it becomes lambda L over epsilon naught. So remember, lambda is equal to the charge Q inside divided by the length. So Q inside is lambda L. So instead of Q inside here, put lambda L, and that's Q divided by epsilon naught. And what happens to L? Gets cancelled. So you get the electric field. L cancels, you bring this over, it becomes lambda over 2 pi epsilon naught r. And remember, what is 1 over 2 pi epsilon naught? We wrote this in terms of k, right? In previous chapter, becomes 2k in the numerator. So you can write this way, or you can write 2k lambda over r. Either this or this. This is for infinitely long line of charge. Line of charge with linear charge density lambda at distance r from the line. So you see, in this case, it's a lot easier to calculate this than the Coulomb's law. Remember, in Coulomb's law, we integrated and we found general formula. We need to do all of that, but here it becomes very simple. So that's the power of Gauss law. It has some advantages and some disadvantages. Sometimes if you have symmetry in the problem, it makes your calculation very simple. But if you don't have symmetry in your calculation, you can't use it. As simple as that. For example, over there we did for a short piece of line of charge. You cannot use Gauss law for that because there's no symmetry. You cannot say, for example, at different points here, the electric field is the same. Which is not. Right? If you don't have symmetry. Only for infinitely long one, you can say that there's a symmetry. Another problem that you can solve easily with the Gauss law, what if you have a thin spherical shell of charge Q? Let's say charge Q is uniformly distributed over a spherical shell. You want to find the electric field inside and outside. This is, by the way, possible to do with integration, and it's a little bit tedious to do the integral, because you have to do at least two-dimensional integral, and this is the problem. I don't know where I heard it, but Newton had this problem. He realized the law of gravity, and he realized that for a spherical object like the Earth, if you want to calculate the gravity of the Earth on any other object, you can put all mass of the Earth at the center and consider the point object, and use the gravitational formula, G m1 m2 divided by r squared, to find the force between the two. But he couldn't prove it. This is extremely hard to prove unless you know really well how to integrate in 2 dimensions or 3 dimensions. And Newton kept this law of gravity secret for 20 years. He knew it. He didn't tell anyone because he didn't like criticism. He couldn't answer, okay, if we have the Earth, we can put all the mass at the center and calculate like a point mass. And because he couldn't prove this, he didn't tell anybody about the law of gravity until he invented calculus. And after 20 years, he could prove that, and then he told everyone about law of gravity. Can you imagine knowing something that important, not telling anyone for 20 years? Because you can't answer one question. Newton found out that if you have a spherical shell, there's no gravity inside. Because he said, you see, if you take this point, you make that cone that I said, that cone like this. He said that the gravity of this and gravity of that are exactly the same and the opposite direction. So they cancel the effect of each other, and then move the cone around. You get total net gravitational field of 0 inside the spherical shell. He could prove for inside, but he couldn't prove for the outside. And that requires tedious integration. And I have done it, but I don't know, maybe I presented in another video. And you can find it in some books. But not in this book, I think. Anyway, now, with Gauss law, it is very easy. See how we can use Gauss law to do that. Suppose you want to find the electric field at this point. Then you want to use the symmetry. You use a Gaussian surface that is centered at this center of this surface, and it is a sphere. Like this Gaussian surface. And you know that integral of E dot dA equals the total charge inside over epsilon naught. But you said, you know that total charge inside is 0, right? But that doesn't tell you necessarily that the electric field is 0, because it says integral of E dot dA is 0. But because of the symmetry, you can say that if there is an electric field, it should be in the radial direction. Because if it is not in radial direction, it has some azimuthal direction or parallel to the surface component that makes this direction, for example, different from the other direction. But there's no distinction such as that. So the field has to be radial, either outward or inward. All right? So the field is either in the direction of dA or in opposite direction of dA. So E dot dA becomes simply E times dA, positive or negative. But let's say just becomes integral of E times dA equal to 0 over the surface. And again, because there's no distinction between any direction, electric field, if there is any, should be the same in all directions. So this E comes out of the integral. E times integral dA should be equal to 0. Right? And then the integral of dA is the area. Area is not 0, therefore electric field is 0. inside. So this is something Newton could find out even though he didn't know about Gauss law, right? Gauss was a lot later than Newton. But when it is outside, it is a very hard question, hard problem, and you can still use Gauss law to calculate that. What is the electric field outside? Again, for outside, if this is your sphere of charge Q, then you're calculating the electric field at this point or this point. You make a Gaussian surface with that radius. The spherical. Again, argue that if there is an electric field, it should be radial only, and the same at any point around on this surface, right? Gaussian surface. So if there's electric field, it should be this way. If the charge is positive, of course, it's away from the surface, sphere. So E is this way, and dA is also, dA is the same way. And then, again, you say integral E dot dA, integral of E dot dA equal to Q inside, which is total charge here, divided by epsilon naught. And then you say E and dA are in the same direction, becomes integral of E dA, E times dA, magnitude only. And then E is the same everywhere on the surface, so E comes out, becomes E times the integral of dA is Q over epsilon naught. And then integral of dA is just total area, which is 4 pi r squared, right? Now if you are at distance r, you get 4 pi r squared E equal to Q over epsilon naught. Then E becomes what? Q over 4 pi epsilon naught r squared. And 1 over 4 pi epsilon naught is K, so we can write it as KQ over r squared, which is Coulomb's law for point charge. Means that you can put all this charge at this point and just calculate the electric field of a point charge if it is a spherical symmetry. You see, that problem that took Newton 20 years to do becomes this simple when you use Gauss law. Of course, Gauss was a lot later than Newton. That's why Newton couldn't just do all of this. He was genius, but couldn't do all of this because Gauss was a genius by himself, but he was 100 years or so later. All right, so the conclusion is that if you have a spherical shell that has a uniform charge distribution on the shell, inside the electric field is 0. Outside the electric field is like you put all the charge at the center and calculate the electric field of a point charge. That makes it very, very simple to use.